All right, today we're cracking open what is basically the original blueprint for the internet. We're going to go all the way back to 1974, to this one paper by Vint Cerf and Bob Kahn that, well, it pretty much wrote the rulebook for how our entire digital world talks to itself. So yeah, let's get right into it. I mean, just stop and think about that for a second. This was before the web, right? Before email was a thing for most people. Before all the stuff we totally take for granted today. These two guys, they had to sit down and imagine this future where all these computers were connected, and then they had to write the instructions to actually make it happen. Wild.
Okay, so to really get why this paper was such a game changer, we have to understand the mess they were trying to clean up. What did the digital world even look like back then, before their big idea?
Well, for starters, there wasn't one internet. Not at all. Instead, you had a bunch of these really advanced but totally separate computer networks. You've probably heard of the most famous one, ARPANET, and they all use this cool tech called packet switching, basically sending data around in these little digital envelopes called packets. Each network was its own little masterpiece of engineering, its own little digital island, doing amazing stuff, but only within its own borders.
And that was the giant, glaring problem. You see, these islands, they couldn't talk to each other at all. It was kind of like trying to make an international phone call, but every single country had a completely different, totally incompatible phone system. It just wouldn't work. It was a total non-starter because each network was speaking its own private digital language.
And the reasons why were, well, they were all over the place. It wasn't just one little thing. I mean, how you'd address a computer on one network was completely different from how you do it on another. The biggest chunk of data you could send, the packet size, that was different too. How they handled errors, when they decided a connection was lost. You name it, it was different. It was just a total technical Tower of Babel, a complete mess.
So, staring at this absolute wall of problems, Cerf and Kahn came up with a solution that was just so incredibly elegant. See, they realized they didn't have to rebuild all those different islands, they just had to build bridges between them.
And this quote from the paper itself, it just perfectly sums up their whole way of thinking. Basically, they're saying, look, it would be way easier and cheaper if we could just solve all these differences right at the edges, at the boundaries where the networks meet. Don't force everyone to change their internal systems. Let's just build a clever translator for the border.
And this really lays out the two choices they had. On one hand, you have the hard way. And trust me, this would have been a political and technical nightmare, trying to get every single person to scrap their system and agree on one new standard. Good luck with that. Then there was the smart way, their way. They said, let's just create a new protocol, a new layer that sits on top of everything else. A common language that everyone only has to speak at the borders. Inside their own network, they can keep doing whatever they want. Genius.
So that word, protocol, it's the key to this whole thing. And all it really means is a set of rules that everyone agrees on. It's basically just grammar and vocabulary for computers. By creating this one shared protocol, they were essentially inventing a universal language that all these different networks could use to finally talk to each other.
All right, so the first major piece of their solution was this special little box. A device, hardware and software, that would sit right at the edge of each network. And its whole job was to be that universal translator we've been talking about. In the paper, they called it a gateway. Now, you and I, we know this thing is a router, but the idea is exactly the same. It's the traffic cop for the internet standing at the intersection and telling all the little data packets which way to go to get to the next network.
So let's actually trace a packet's journey, just like they drew it out in the paper. Imagine your computer, process X, is on network A, and it sends a message. That packet travels to the first gateway. The gateway grabs it, reformats it so network B can understand it, and sends it on its way. It zips across network B, hits another gateway, which does the same thing, reformats it for network C, and finally, boom, it arrives at its destination, process Y. The gateways do all the heavy lifting, all the translation.
Yeah, that universal translator analogy is honestly perfect. Think of each network as a country with its own unique language and customs. The gateway is that person at the border checkpoint who takes your message, translates it, stamps the right papers for the next country, and makes sure it gets through without any issues. But, just getting the packets across the border, that was only half the battle. The computers on either end, the sender and the receiver, they needed their own set of rules for handling all this data. And that brings us to the second massive piece of their invention, a bit of software they called the Transmission Control Program, or TCP. So here's a really practical problem they had to solve. What happens if your network likes to send out big, chunky packets of data, but the next network it has to cross can only handle tiny little ones?
What do you do?
Well, the gateway does something called fragmentation. It basically acts like a Cuisinart and just chops that big packet up into smaller, bite-sized pieces that the next network can handle. But, and this is the really clever part, the gateway doesn't bother putting them back together. Nope, it leaves that job to the computer at the final destination. This became a core principle of the internet: keep the network itself as simple as possible, and put all the smarts at the endpoints.
Okay, but that creates a whole new problem, doesn't it? Because these little pieces, these fragments, they don't necessarily all take the same path. Some might take a super fast route, others might get stuck in digital traffic, so they can all arrive at the destination completely out of order.
Which means your nice, coherent message could end up looking like total gibberish. You order, hope arrived in this eye. Yeah, that's not exactly what you were trying to say. So how on earth do you fix that?
The answer is just so simple and so brilliant: sequence numbers. Basically, every single tiny piece of your original message gets its own unique number. It's like numbering the pages of a letter before you send it. That way, even if the packets show up all mixed up, the computer on the other end just looks at the numbers and goes, okay, number 1 goes here, number 2 goes here, and puts it all back together in the right order. Easy.
And that brings us to the last big piece of the puzzle: reliability. What if one of those packets just gets lost? Poof, gone. Well, the protocol has a really smart system for that. When the sender sends a packet, it also starts a stopwatch. When the receiver gets the packet, it immediately sends back a tiny little message that just says, "Got it." They call it an AK for acknowledgement. If the sender's stopwatch runs out and it hasn't heard back, it just shrugs and says, "Well, I guess that one got lost," and sends it again. It's simple, it's tough, and it works.
So let's step back for a second. How did all these ideas from, a 50-year-old academic paper end up building the world we're all living in right now? Because make no mistake, these principles aren't just some historical curiosity. They are the living, breathing foundation of pretty much everything we do online. And here's a little detail from the paper that I think is just amazing. When they designed this thing, they built the addressing system to handle a grand total of 256 networks. And they wrote that this should be sufficient for the foreseeable future. Can you even imagine? 256. At the time, that probably seemed like an enormous number. Today, of course, there are millions upon millions of networks. It just goes to show you the unbelievable scale of the thing they set in motion.
I mean, the impact is just hard to wrap your head around. The paper comes out in '74. It takes about another 10 years for their protocol, which, by the way, eventually got split into 2 parts, TCP and IP, which is why we call it TCP/IP, to become the official standard. Then, in the '90s, the World Wide Web gets built right on top of that foundation. And now, today, every single thing, your phone, your laptop, your smart TV, even your fridge, they all use the exact same core ideas from that one paper to connect to the internet.
And that really just leaves us with one big, fascinating question to chew on, doesn't it? Cerf and Kahn wrote the rules for our digital world way back in 1974. So what's the equivalent that's being written right now? What papers are being published in some lab or university today that are quietly building the foundation for a future that we can't even begin to imagine? What's going to be the TCP/IP of, say, 2074? It's pretty wild to think about.